Now we have maintainability functions. You remember I told you in my previous video that what is maintainability. So let's have a look what is maintainability. Maintainability we have, it can be defined as the probability of repairing a failed component of the system at a specific time bounded between 0 and 1. So what is this? This is just basically the probability of repairing our component. Okay, the component that has got failed, so it is the probability of repairing that component over a specific time, and it is also bounded between 0 and 1. So this is basically the repairing procedure. Got it? So now maintainability functions. Maintainability is represented as m of t, and it can be represented in the form of PDF. Okay, probability density function. It is represented in the form of PDF, and it can be in the form of exponential, Gaussian, or log normal. So these are the forms that it can be in. So okay, now let's see. We say that our maintainability at time t is the is in the form of PDF. Remember, because we have according to the definition we say that it is the probability of repairing a failed component. So that's why we are taking it as PDF. Now ft of t is equals to mu e at the minus mu t. Ft of t is our probability. This is the probability term. And what is its definition? What is its formula? It's mu e exponent. First we are talking about exponent, so that's why in the form of exponent, so that's why we have taken this formula for probability, and for the exponential form we have this formula. So mu e at the minus mu t, and what we have mu here, mu is the number of repairs over time, 1 over hours. This is the unit. So mu is the number of repairs. You remember we have mu in the Markov chain, where we consider mu as the repair, and lambda was the failure rate and mu was the repair rate. So here also mu is the number of repairs over time. This is the repair rate. Got it? This mu is the repair rate. Now what we say, we have MTTR. What is MTTR? Mean time to replacement. We have MTTR because we are in the procedure of repairing our failed component. So that's why we have the formula for MTTR, that is 1 over m, where sigma I going from 1 to n and t of I. Okay, got it? And what we have, ti is the limit from t1 going from t1 t2 to tn. So ti can be t1 t2 to tn. So that is the ti here. This ti is this, and mu is mu is also known as the 1 over MTTR. You remember in our Markov chain, in our availability function, we take mu as 1 over MTTR, 1 over mean time to replacement, because we are talking here about replacement. Maintainability is basically the replacing of a failed component. So that's why we are taking these terms here. We are taking mu and we are taking MTTR, and we say that we have an MTTR that is 1 over m sigma I going from 1 to n and ti. Okay, now what we say, we have a probability that our t is less than equal to small t. So we say that we have a probability that our capital T is less than equal to small t. So what it means when we say that capital T is less than equal to small t? So less than, that means from 0 to equal to, so that means we have a limit of t. So our capital T is from 0 to t. Got it? This limit, how we create this limit here? That is less than equal to t. So from 0 to t. For equal we have t here, and for less than we don't know what is in between the less than, or it can be any number. So we have taken from 0 to t. We have taken this term, this limit here. And what's next? We say probability is t less than equal to t. So for that we took here, remember, we say our probability is in the form of this. our probability, what was our ft of t? It was ft of t was this. So this is capital T, and we are talking about now this capital T. So that's why we have to write the probability here, f tau and d tau. So we have a limit going from 0 to t, f tau and d tau. And what we do now, in the place of this f tau, this ft of t, we write this thing here. This comes here, and d tau remains the same. You got it? Because we are saying that our probability is p capital T less than equal to small t. So capital T, and where we wrote capital T, we wrote capital T here. So that's why this thing comes here, and in the replacement we got this term. So it is from 0 to t, mu e minus mu tau. This t is being represented because we are now in the integration of d tau and tau. So that's why we have replaced this t into tau, and this d, and this is d tau here. It comes here, and now we are going to integrate this function. And by integration, what we got, we say this is mt is written because remember we say that our mt is equal to our PDF. So that's why we can write either this, we can write this is equal to m of t. So we are going to find our maintainability function here at time t. So after integrating, due to integration, see, this minus mu comes in down, and this got cancelled. So what remains? This thing is remaining here. Minus, this minus comes here, minus e at the minus mu tau, and the limit going from 0 to t. Now we are going to put our limit. So this minus comes outside, and e minus mu t, because we have first limit of t and the other limit of 0. So now this remains here, and e to the minus 0 or plus e to the 0 is 1, you know that, and this minus got multiplied, so minus and minus minus becomes plus. So now what we got now, our final mt is equal to 1 minus e at the minus mu t. This is our final function for maintainability. So we have done it for the exponential form. Now we are going to, I'll also be giving you an example for the log normal one, log normal one. Okay, so what we have for the log normal one, we have mt. Now we say that first we talk that our mt was, our maintainability function was a PDF. So a PDF, it is always the PDF, okay, but we just are changing our forms. First we talk about exponential, now we are going to talk about log normal. So PDF remains same, and ln comes here. Now what would be the what's going to change now? See, this mttr becomes, it's the same as it was, just as it was here. It's just that this ti is being replaced with ln ti. Okay, 1 over m sigma I going from 1 to n ln ti. This is just replaced by this, and we put this whole term, we take this whole term as t, capital T, and this is a small sign here. So we take this term as in the way of this. Okay, it's, we have put here because the reason behind is because this thing and this thing don't get interconnected, and they don't get, you know, mixed. So that's why we have put this thing here. And what is this? We have this is a random variable. Okay, just we have taken a random variable, and its limit is also from t1 to t2 and so on tn. It's a random variable. So that's why we have considered our equation as in the form of this. Now what we talk now is, in this here we are, what we are doing, we are taking sigma square, and you know that what is the formula for sigma square? We have 1 over n minus 1 sigma I going from 1 to n, sum of I going from 1 to n ln ti minus t, and this t is the average here. This t is the average. Okay, so our sigma square is equals to 1 over n minus 1 sum of I going from 1 to n ln ti. So this is now being replaced is now being represented in the form of this ln ti minus t, and this average, because we have t, this t is the average. This t was the random variable. Don't get confused in both of the t's. This t is the that has the sign of like this. It is a random variable, and this t that has a sign of like this, it is an average value. Okay, and sigma square, so that's why it can be represented in the form of this. So we have square here. And now what we say that we have a probability of t less than t0. First we say our t is less than equal to t, so this was the probability for an exponential form, and now for log normal form we have a probability of p, that is t less than t0. And what is t0? I'll tell you later that what is this t0. Okay, so this sigma now can be written in the form of like this z1. Why we take z1 here? Because we are talking about for the first term, when we are in the first period, when we are I, that is in the one period. So that's why we have just shown here for the one part we have take sigma 1 equals to ln t0, because we say that our capital T is less than t0. So that's why we have put here ln t0 minus, and this remains the same. And we were doing for sigma square, so that's why it was square here. And now this sigma goes down, and what we got now, the square is removed. Okay, so this was just that was for variance sigma square, and now we are doing for z1. So that's why there would be no square thing present. So z1 is equals to ln t0 minus t, this average, over sigma. So this is the way of writing our log normal PDF empty function. Okay, this is the way of writing our empty function in the form of log normal PDF. So that's our final answer. And now we have a numerical. What we have a numerical? We are talking now about the unrepaired failures. What are the unrepaired failures? That means that what are the items that need to be repaired, and they are in the form of unrepaired items. Okay, so now we are going to find the items that are unrepaired, because you know that for maintainability we say that maintainability is the probability of repairing a failed component. So first we have to find that what are the components that are failed and that are unrepaired, so that we can find the unrepaired components and we can do the maintainability function there, and we can repair them. So first we have to find it is necessary to find the unrepaired components. So what is the procedure of finding this unrepaired components? We have T0. T0 is time of ending of failures. I told you what is this T0. This T0 was here. It is basically the time of ending of failures. Okay. So suppose our system, we have a component, it gets failed. So T0 is the time when it fails. So the time that it got failed, the ending time of that failure. Okay, the time it has failed, and that is the ending time. So T0 is basically the time of ending. So the component, when it has completely failed, that time is being measured, is being represented as T0, time of ending of failures. Okay, all the failures why we have written failures, because all the failures have been done. Now the overall time that is of the failures being done, so it is represented being ended, so it is represented by T0. And we have lambda. You know, is the failure rate, number of failures that I am expecting to occur in the unit of time. Okay, so how many number of failures, how many more you can expect, okay, in the period of time, in the unit of time, how many more failures can be expected. So that is here we are going for lambda, because we will be talking about everything, because you know, for repairing for calculating the number of unrepaired items, for that we have to know that, and we have to take every constraint, every condition, we have to take every condition for calculating the number of unrepaired items. So that's why we are talking about T0, we are talking about lambda. We have to find the first that what is the time the components has failed, and the ending time of that component, ending failure time of that component. We have to take this as well, and we have to take lambda as well. And what is lambda? Lambda is basically number of failures. So what is more to be expected? We suppose we have a circuit, we have a system, and what is more can be expected to be failed in that system? What more? Because as time will pass, there will be more and more failures, and more and more components can be failed. There is a chance of failing more and more components. So that's why we have lambda for number of failures that I'm expecting to occur in the unit of time, and we will be giving a unit of time. We will be giving a specific time for that. Okay, we have to give the specific time. We have to consider our lambda for a specific time. So this, both the terms will get multiplied and empty. We are finding here the number of unrepaired items. So you remember that for the exponential form, we have mt equals to 1 minus e at the minus mu t. Okay, this is our mt for our, this is our maintainability for our exponential form. So this one comes here, and we have the equation in the form of like this. Okay, what we got, you remember, we got the maintainability as 1 minus e at the minus mu t. This was our maintainability for an exponential form. So here we have a maintainability for our exponential form, and this one comes here, and this thing remains. Maintainability is basically the probability of repairing a failed component, but here we are not repairing a failed component. We are not repairing here. What we are doing, first we are finding the number of items that are unrepaired. Okay, we are finding this. So that's why we have taken this 1 minus at the other side. That's why we have taken this 1 minus at the other side, because maintainability is probability of repairing a failed component, but here we are not finding the probability of repairing a failed component. We are finding the number of items that are unrepaired. Okay, first we are doing the initial step. So that's why this 1 minus would come here. It means that 1 minus mt means that we are not repairing our failed component. So that's why its formula becomes in the form of like this. Okay, now we say that number of items unrepaired for at TR. So what is this TR? This TR is basically the repair time. Number of failures unrepaired, TR. So we will represent our this whole scenario, and the thing that we need to find out, that is number of items unrepaired. So this all thing will combine, and we will get the equation, the formula in the way of this, in the form of this, that is lambda T0 e at the minus mu t. Lambda T0 e at the minus mu t, and I told you that we are for TR, repair time. So that's why we have wrote it TR here. And what is lambda? Lambda, lambda is our average failure rate. T0 is our time of ending of failure. So that is, lambda is given 0.1, T0 is given 12 months. This is the system life. Okay, time of ending of failures, like when the failures has got ended. So this is our system life of our system. It is 12 months that we have, that failures have ended now. Now there would be no failures. Okay, so that's why the time the failures ended. Okay, now this is the time all the failures had been ended, so there would be no failures further. So that's why we have 12 months. This is, we can be we can approximately assume that this can be our system life, that our system will work, will live for 12 months more. And we have mu, that is the repair rate, mu is the repair rate, and tr I told you is the repair time. So tr is given as 2 hours and repair rate is given as 0.5, and we just put the values. What is this? Number of items unrepaired is represented in the form of NUT, and we have put the formula here. Lambda comes 0.1, this 12 comes 12 here. These are the 12 months, and E at the minus 0.5, mu is 0.5, and TR is 2. So this thing multiplies and we got NUT as 0.4415. So this is our number of items unrepaired. We have got the answer for this. That was an easy one. That was nothing. So that's all for now.